So for part two, we're going to be looking at redox reactions and how different functional groups that we've already had a look at actually relate to these redox reactions. So we'll see that you can actually switch from one functional group to another using these redox reactions that we're going to have a look at. And one of the main ways we're going to display the importance of these redox reactions is looking at how alcohol is actually broken down in the liver, because there's actually two redox reactions that we rely on to break down ethanol that's present in alcoholic beverages into an acetate compound, also known as ethanoic acid, which can actually be metabolized by the body and is non-toxic. So before we get on to how the redox reactions will break down alcohol, we're going to review some of the detail of redox reactions and work out what's happening here in a redox reaction. So remember, one example of a redox reaction we've seen in the past is combustion reactions. So a combustion reaction where a component like a hydrocarbon is burning in the presence of oxygen is actually a redox reaction where oxygen is being reduced, and in this case the methane is being oxidized. So we always know that a component is being oxidized when it's losing hydrogen. So if you compare the carbon on both sides of the equation here, initially on the reactant side it has CH4, and on the product side the hydrogens are now gone. So to go from here to here, it has lost hydrogen. And we know that losing hydrogen is equivalent to being oxidized. So in a redox reaction, one component is always oxidized and one is reduced. And that means in this case that the oxygen has been reduced. And we can see that one of the oxygens here actually now has hydrogens attached to form water. So to go from something that doesn't have hydrogen to go to something that has hydrogen, that means that the oxygen has actually accepted hydrogen. Okay, so that's a hallmark of the redox reaction. One component is losing hydrogen, which is equivalent to losing electrons, and one is gaining that hydrogen. So you can imagine that that hydrogen is basically being taken off the carbon and added onto the oxygen instead. So as I said, all combustion reactions are redox reactions. So let's look at the nitty-gritty of what's happening in a redox reaction. So as I said, we've got these two processes occurring simultaneously. So we've got oxidation and reduction. So in the definitions, it can either be considered loss of electrons, gain of electrons, or loss of hydrogen atoms, gain of hydrogen atoms. You can also think about it in terms of loss or gain of oxygen atoms, but we're going to be focusing mostly on loss or gain of hydrogen atoms. When you lose or gain a hydrogen atom, that is equivalent to losing or gaining electrons, because each hydrogen contains one proton, which is one positively charged subatomic particle, and also one electron. So by losing or gaining a hydrogen, you're actually losing or gaining electrons as well. So for oxidation, this is where there's the loss of one or more hydrogen atoms, whereas reduction is the opposite. The compound will be gaining one or more hydrogen atoms. So as I showed you at the top here, we've got a hydrogen atom being composed of one proton and one electron, which means that losing electrons is losing hydrogens is equivalent to losing electrons, just like gaining hydrogens is equivalent to gaining hydrogen. And we'll see that oxidation and reduction always occur together, because you need one of the reactants to be the component that's losing the hydrogen, and the other component is going to be the one that's gaining or accepting the hydrogen. So it's just like in an acid-base reaction where you need one component that is losing and one that is gaining. So you can't have one without the other. So in the earlier lecture we saw this handy rule for remembering what oxidation and reduction actually mean. So this oil rig can tell us what each one does. So the oil letters is comes out as oxidation is loss, and what we're losing is electrons and or hydrogen atoms. So we're going to be focusing on the loss and gain of hydrogen atoms. So we can just think of oxidation as the loss of hydrogen atoms, whereas the rig part of it is reduction is gain. And what are we gaining? We're gaining hydrogen atoms. So if you're ever having trouble remembering what the difference between oxidation and reduction is, just think of oil rig, and that should help you remember that oxidation is loss and reduction is gain. So here we have a redox reaction at the top here. It's actually the redox reaction I showed you on the combustion slide, remembering that all combustion reactions are redox reactions. So as we know, one reactant is going to be oxidized and one will be reduced. So to determine which is which, essentially look for the non-hydrogen atoms on each side of the equation. And this will help you to work out which ones have lost hydrogen and which ones have gained hydrogen. So if we look at the CH4 here, the CH4 on this side matches up to the CO2 on this side because they both contain the carbon atoms. So that's one pair. So that means the other pair has to be oxygen pairing with our H2O. So now that we've got our pairs, we can actually work out how the CH4 turned into CH2. Did it do this by gaining or losing hydrogen? And we can do the same for the oxygen. So to go from CH4 to CO2, the CH4 has actually lost hydrogen, and hence we can say it's been oxidized. Where have those hydrogens gone? Well, they've been accepted by our O2, and because it's accepting the hydrogen, we can say that it's been reduced. So redox reactions are very important processes to metabolic pathways, and one of the key components to this is coenzymes like FAD. We'll see a lot more of these in the metabolism section of the course. But essentially what the coenzymes can do is they can actually behave as the component that's going to accept the hydrogens off a biological molecule, for example, a carbohydrate or a protein, whatever's being modified in the chemical reaction. And what makes these coenzymes even more special is they can actually be the hydrogen donators as well. So not only can they accept hydrogen from biological molecules, they can also donate hydrogen to biological molecules as well. So that essentially means that they can either oxidize or reduce a different reactant that they're reacting with. So in this case, the FAD is actually gaining hydrogen. So we can see that that means that the other component, which is the biological molecule shown in orange here, must actually be losing hydrogen. And you can see that signified by these arrows here. So we've got the two hydrogens coming off the orange biological molecule and being moved onto the coenzyme. And we can see the result of that on the product side here, where we've got the coenzyme with the additional two hydrogens. So because the coenzyme accepts those two hydrogens, it now becomes FADH2. And to go from FAD to FADH2, meaning it's gained two hydrogens, corresponds to the compound being reduced. So we've got this same pattern where one reactant is oxidized, losing hydrogen, and the other is reduced, which gains hydrogen. So as I said, redox reactions are very important to different metabolic pathways. Many of those that we rely on to generate cellular energy, which is our ATP, actually have redox reactions as part of these pathways. Things like glycolysis, the citric acid cycle, the electron transport chain, all have one or more redox reactions within that process. And the one we're going to be looking at today is how alcohol is actually broken down in the liver. And this relies on two of these redox reactions where coenzymes are actually used to oxidize the compound. Firstly, ethanol will be oxidized, and then a second compound called acetaldehyde will be oxidized as well, eventually producing the non-toxic acetate. So what's so great about these coenzymes is they can actually exist in either an electron-rich or an electron-poor form, also corresponding to hydrogen-rich or hydrogen-poor. So in the reaction I just showed you, where it was FAD reacting with the biological molecule, the FAD is considered to be electron and hydrogen poor because it has less hydrogens than the other version of the coenzyme, FADH2. And it can actually switch between these electron and hydrogen rich and poor forms by participating in redox reactions. So to go from FAD to FADH2, has the coenzyme turned into the electron poor or the electron rich form? Well, because it started off as FAD and it accepted two hydrogens, it actually becomes the electron and hydrogen rich FADH2. It would also be possible for that FADH2 to participate in a redox reaction where it actually gives away hydrogen and becomes FAD. And in this case, it would be oxidized by a different reactant that it's reacting with. So in this case, it's actually losing hydrogen and therefore becoming electron and hydrogen poor. So that's the magic of these coenzymes. The fact that they can exist in these two different forms, and this allows them to participate in lots of different redox reactions and interact with important biological molecules to facilitate processes. Again, we'll see details of more of these reactions when we get into the metabolism session, but we will be having quite an in-detailed look at how these redox reactions are going to be able to assist in the breakdown of alcohol in the liver. So here we have an example of when the coenzyme is going to interact with a compound, in this case malate, which contains hydrogen. So it's going to be a redox reaction, meaning one component will be oxidized and one will be reduced. So the malate will turn into oxaloacetate, and notice now that the hydrogen is not attached, meaning it's actually lost hydrogen to turn from malate into oxaloacetate. So we can say that the malate has actually been oxidized. Whereas the coenzyme, in this case NAD+, is actually going to accept the hydrogen from malate. And we know that when something accepts hydrogen, that means it's being reduced. We can see that the result of that is that the coenzyme turns from an electron poor form into the electron rich form. Because remember that accepting hydrogen is equivalent to accepting electrons, because each hydrogen contains an electron. So we've turned the coenzyme into an electron rich form via a reduction reaction. So this has all of the hallmarks of a redox reaction that we need to be aware of for this session. A coenzyme participating in a redox reaction, in this case being reduced, gaining hydrogen from the reactant compound. And as a result of this, the compound, in this case malate, is being oxidized. So this is the same pattern as we'll see with the alcohol breakdown reactions, where a coenzyme NAD+ is actually reacting with the alcohol compounds that need to be broken down. So before we get onto the alcohol breakdown, I just want to show you the difference between a couple of functional groups and what dictates whether they will be oxidized in a redox reaction or not. So the aldehyde functional group, which has a single R group, double bond oxygen, and a hydrogen, actually has a hydrogen atom within the functional group atoms, and that means it has a hydrogen that can be lost in a oxidation reaction. So if it has a hydrogen that can be lost in the oxidation reaction, would this allow the aldehyde to be oxidized or not? Yes, it would, because it has a hydrogen that can be lost, and that's what happens in oxidation. So in theory, the aldehyde compound can actually be oxidized, and that's what we can see in this representation down here. We've got the aldehyde group, and the hydrogen within that group can actually be lost via an oxidation. It can be donated to another compound. And once this happens, then there's space for an OH group to come in and attach to the carbon to make sure it has 4 covalent bonds. So when an aldehyde group is oxidized, the functional group actually changes into another functional group. So that functional group now contains a carbonyl group and an OH group, which is a carboxylic acid. So to summarize, the aldehyde can be oxidized by losing hydrogen, and that converts the aldehyde into a carboxylic acid. What about the ketone though? Let's have a look at the ketone atoms. So ketone was C double bond O like this, and 2 R's. Does the ketone group have any hydrogens? No, it doesn't. It's only got the carbon and the oxygen here. So this means that the ketone actually cannot be oxidized. So why wouldn't the ketone be able to be oxidized? Essentially, it comes down to the lack of hydrogen atoms. A compound can't give away hydrogen atoms if it doesn't have any hydrogen atoms. Just like someone can't give away money if they don't have any money. Okay, so you have to have the component to be able to give it away. And because the ketone group can't give away hydrogen atoms, therefore it can't be oxidized in a redox reaction. So we can say that ketones will resist oxidation in a redox reaction in comparison to the aldehydes, which are going to be readily oxidized. So here's an example of a ketone compound where we've got the ketone group in the middle here, and on each side is carbon atom attached corresponding to the R group. And we can say that this resists oxidation because the ketone group here has no hydrogen within that to be donated. There are hydrogens on either side, but that's not part of the functional group. And remember, the functional group is the most reactive part of the compound in general. So we can say that the ketone group in this case won't be oxidized. Alright, so now we've reached the point in the session where we can have a go at a couple of revision questions. So remember, these questions are available in the revision quiz under the specific weeks tab on the LMS. So I encourage you now to pause the recording and have a go at the first 2 questions to make sure you've understood what we've gone through so far in this session. Alright, so the moment some of you have been waiting for, I'm sure, we're actually going to learn in detail how the alcohol is going to be broken down in the body. So the specific compound we're talking about here is ethanol. So that's the compound that contains the alcohol functional group that has 2 carbon atoms. So I'll just quickly draw the structure here. So we've got 2 carbon atoms, 1 attachment to an OH, and we've got another couple of hydrogens here to make the bonds up to 4, and 3 hydrogens on this side as well. So the body doesn't need ethanol for anything. It can't really use it for anything in particular. So essentially, the body treats ethanol as something that it needs to get rid of. So how does it get rid of it? Well, it takes it to the liver to be broken down into something that can actually be used by the body. So essentially, once the ethanol is in the bloodstream, it'll be trafficked to the liver so it can be broken down. So remember, ethanol itself is actually toxic to the body. So there's no need for the body to actually keep the ethanol compound. It's going to do whatever it can to get rid of it. So to do this, it has to take it to the liver. So why do you think that ethanol is trafficked to the liver to be broken down? Well, this is the specific location where the breakdown reactions actually take place. So the redox reactions that break down alcohol only take place in the liver because there's specific enzymes that are needed to facilitate those reactions that are abundant in the liver. So once those redox reactions have taken place, 2 of them, we're then left with ethanoic acid, also known as acetate, and we can say that that's the last breakdown product of that process. So what the body will usually do is actually convert acetate to something even more useful, although the acetate now is non-toxic compared to what we started with, which was toxic. So now that we've got the acetate, it can actually be converted into a very useful compound called acetyl-CoA. Why is it so useful? Well, it can be used in a number of metabolic pathways, and one of the main ones is the common metabolic pathway, which is the main pathway used to make energy in our mitochondria. So our cells have to make enough energy to keep all their processes going and to prevent essentially the whole thing from breaking down and dying. So it's important that we have enough of these compounds like acetyl-CoA to keep the processes going to make sure there's enough energy to maintain the cell. Alright, so here is an overview of how ethanol is actually broken down. So we've got these two separate redox reactions. So you can see a summary in the table down the bottom here. So starting off with ethanol that contains the alcohol functional group, the first redox reaction will cause a functional group change, and we then have a compound called acetaldehyde. And as its name suggests, it actually now has the aldehyde functional group. So another name for acetaldehyde is ethanol. So in this nomenclature, the eth tells us that there's two carbons, just like the original compound had. Eth in ethanol tells us there's two carbons. The OL in this case told us that there was the alcohol functional group, and the AL tells us that there's aldehyde. So acetaldehyde is the more common name, non-technical name for the compound, and that's the one we'll be referring to in this part of the session. So once we've got acetaldehyde, this is a bit problematic because this compound is actually even more toxic than the ethanol was. So why would the body break down ethanol into something that's even more toxic? Seems a bit silly, doesn't it? There is a reason though, because it has to break ethanol down into acetaldehyde before it can be broken down into the next compound, which is non-toxic. And we can see that in redox reaction number 2 here. So once the body has acetaldehyde, it's then converted into acetate via the second redox reaction. And in doing this, we convert the aldehyde functional group into the carboxylic acid functional group. So can anyone think of the chemical name for acetate if it's a 2-carbon compound that contains the carboxylic acid functional group? Well, the S will be at the front because it's a 2-carbon compound, and to dictate that it's a carboxylic acid, it's going to have oic acid at the end of the name. So ethanoic acid is the other name for acetate. So essentially the alcohol breakdown reaction is all about the conversion between these compounds. And in converting between these compounds, we're also changing the functional group. So in each case, the functional group is actually being oxidized. So the ethanol functional group, which is alcohol, is going to be oxidized to the aldehyde functional group, which is present in acetaldehyde. In the second redox reaction, again the compound will be oxidized, this time going from aldehyde to carboxylic acid. So there's 2 functional group changes within this series of redox reactions. So we're going to look in detail how each one of these occurs.